Supervised learning. Learning a class from examples. We discussed supervised learning starting from the simplest case, which is learning a class from its positive and negative examples. We generalized and discussed the case of multiple classes, then regression, where the outputs are continuous. Let us say we wanted to learn the class C of a family car. We have a set of examples of cars, and we have a group of people that we survey, to whom we show these cars. The people look at the cars and label them. The cars that they believe are family cars are positive examples, and the other cars are negative examples. Class learning is finding a description that is shared by all positive examples and none of the negative examples. Doing this, we can make a prediction. Given a car that we have not seen before, by checking with the description learned, we will be able to say whether it is a family car or not, or we can do knowledge extraction. This study may be sponsored by a car company, and the aim may be to understand what people expected from a family car. After some discussions with the experts in the field, let us say that we reach the conclusion that among all features a car may have, the features that separate a family car from other cars are the price and the engine power. These two attributes are the inputs to the class recognizer. Note that when we decide on this particular input representation, we are ignoring various other attributes as irrelevant. Though one may think of other attributes such as seating capacity and a color that might be important for distinguishing among car types, we will consider only price and engine power to keep these examples simple. Let us denote price as the first input attribute, x1, for example in US dollars, and the engine power as the second attribute, x2, for example engine volume in cubic centimeters. Thus we represent each car using two numerical values. X equals to x1, x2, and its label denotes its type. R equals to 1 if x is a positive example, R equals to 0 if x is a negative example. Each car is represented by such an ordered pair XR, and the training set contains n such examples. X is equals to the set x to the t and r to the t, such kind of tuple where t is starting from 1 to capital N, where t indexes different examples in the set. It does not represent time or any such order. Our training data can now be plotted in the two-dimensional x1, x2 space where each instance t is a data point at coordinates x1 to the t, x2 to the t, and its type, namely positive versus negative, is given by r to the t. After further discussions with the expert and the analysis of the data, we may have reason to believe that for a car to be a family car, its price and engine power should be in a certain range. That is, P1, which is less than equals to price, less than equals to P2, and E1, which is less than equals to engine power, which is less than equals to E2. For suitable values of P1, P2, E1, and E2, such an equation that we have mentioned before, P1 and P2, E1 and E2, related to the engine power, thus assumes C to be a rectangle in the price engine power space. So such an equation fixes H, the hypothesis class from which we believe C is drawn, namely the set of rectangles. The learning algorithm then finds the particular hypothesis, little h, H in capital H, to approximate C as closely as possible. Though the expert defines this hypothesis class, the values of the parameters are not known. That is, though we choose H, we do not know which particular little h in capital H is equal or closest to C, but once we restrict our attention to this hypothesis class, learning the class reduces to the easier problem of finding the 4 parameters that define H. The aim is to find a little h in capital H that is as similar as possible to C. Let us say the hypothesis H, little h, makes a prediction for an instance x such that h of x is equals to 1 if h classifies x as a positive example, h of x is equal to 0 if h classifies x as a negative example. In real life, we do not know c of x, so we cannot evaluate how well h of x matches c of x. What we have is the training set x, which is a small subset of the set of all possible x. The empirical error is the proportion of training instances where predictions of h do not match the required values given in x. The error of hypothesis h given the training set x is the errors of h conditioning on x is equals to the summations of 1 times the condition h of x to the t, which is not equals to r to the t, where t is starting from 1 to n, and where 1 of a not equals to b is 1 if a is not equals to b, and such a 1 function is 0 if a is equals to b. A equals to b. In our example, the hypothesis class H is the set of all possible rectangles, each quadruple, p1 to the h, p2 to the h, e1 to the h, e2 to the h defines one hypothesis H from capital H, and we need to choose the best one, or in other words, we needed to find the values of these 4 parameters given the training set to include all the positive examples and none of the negative examples. Note that if x1 and x2 are real valued, there are infinitely many such h for which this is satisfied, namely for which the error e is 0, but given a future example somewhere close to the boundary between positive and negative examples, different candidate hypotheses may make different predictions. This is the problem of generalization. That is how well our hypothesis will correctly classify future examples that are not part of the training set. One possibility is to find the most specific hypothesis S, that is the tightest rectangle that includes all the positive examples and none of the negative examples. This gives us one hypothesis H equals to S as our induced class. Note that the actual class C may be larger than S, but is never smaller. The most general hypothesis G is the largest rectangle we can draw that includes all the positive examples and none of the negative examples. Any little h in capital H between S and G is a valid hypothesis with no error, said to be consistent with the training set, and such h make up the version space. Given another training set S, G version space, the parameters and thus the learned hypothesis H can be different. Actually, depending on X and H, there may be several Si and Gj, which respectively make up the S set and the G set. Every member of the S set is consistent with all the instances, and there are no consistent hypotheses that are more specific. Similarly, every member of the G set is consistent with all the instances, and there are no consistent hypotheses that are more general. These two make up the boundary sets, and any hypothesis between them is consistent and is part of the version space. There is an algorithm called candidate elimination that incrementally updates the S and G sets as it sees training instances one by one. See Michaud 1997. We assume X is large enough that there is a unique S and G. Given X, we can find S or G or any H from the version space and use it as our hypothesis H. It seems intuitive to choose H halfway between S and G. This is to increase the margin, which is the distance between the boundary and the instances closest to it. For our arrow function to have a minima at H, with the maximum margin, we should use an error loss function which not only checks whether an instance is on the correct side of the boundary, but also how far away it is. That is, instead of h of x that returns 0, 1, we need to have a hypothesis that returns a value which carries a measure of the distance to the boundary, and we need to have a loss function which uses it, different from one dot function that checks for equality. In some applications, a wrong decision may be very costly, and in such a case, we can say that any instance that falls in between S and G is a case of doubt, which we cannot label with a certainty due to lack of data. In such a case, the system rejects the instance and defers the decision to a human expert. Here we assume that H includes C. That is, there exists little h in capital H such that the expectations of little h conditioning on x is 0. Given a hypothesis class H, it may be the case that we cannot learn C. That is, there exists no little h in capital H for which the error is 0. Thus, in any application, we need to make sure that capital H is flexible enough or has enough capacity to learn C.